On September 1st last year, a group of 16 scientists made a discovery that sent shock waves through the scientific community. The importance of their discovery cannot be overstated, as it could change everything we thought about the world. Using the powerful James Webb Space Telescope, these scientists have discovered distant galaxies that challenge astronomical understanding. Before this discovery, it was widely believed that the universe had a period of rapid expansion followed by a cooling phase. This cooling phase eventually gave rise to the first stars and galaxies in what scientists call the Dark Ages. However, the galaxies found by the team appear to be more evolved, similar to our own Milky Way, and indicate a level of maturity beyond what was predicted. This revelation is more than just a mistake. This suggests that these ancient galaxies predate our own, challenging traditional theories of the universe's origins. The consequences of this discovery are profound. The idea of the Big Bang as the true beginning of our universe has been rejected. While the Big Bang theory posits a singular event as the beginning of all matter and energy, the existence of these ancient galaxies points to a more complex timeline. This is not the first time in history that our understanding of the world has changed. Before the early 19th century, scientists believed that the universe was stable and unchanging. This belief was disproved by the observations of Vesto astronomer Melvin Slipher, who observed some nebulae showing a faster movement than ours, which was initially attributed to the movement of our own galaxy. However, other observations, particularly from the Lake Observatory in Arizona, contradicted this explanation. The revolution in our understanding was Edwin Hubble, who showed a clear connection. The farther away the nebula is from us, the faster it appears to be moving. This experimental evidence was consistent with Albert Einstein's theory of general relativity, which showed that space-time can expand or contract. By tracing the universe's expansion back through time, scientists came up with the idea of a singularity, a place of infinite density and temperature from which all matter and energy originated. This particular phenomenon is associated with an event known as the Big Bang. But it raises deeper questions. What happened before the Big Bang? Is there nothing, no space and time? Or is there a place in the history of the world beyond our current understanding? To visualize this, think of the world as the surface of a balloon. As the balloon expands, the objects marked on the screen move away, illustrating the concept of world expansion. A scale, similar to the ruler used to measure the size of a balloon, is used to measure the size of the world. Now our world has scale, but before it was much smaller. As the universe expanded, galaxies and other celestial structures moved away from each other due to the expansion of space. In the future, the scale of the world will continue to increase, reflecting the continued expansion of the world. This view reveals the complexity of the world's history and invites further exploration and research into the mysteries surrounding the origin of the world. But if we reverse this expansion, like letting air out of a balloon, everything on the surface begins to move closer. Finally, if the balloon is fully inflated, it will have a small, flat rubbery appearance. It's like the concept of singularity, a time in the history of the world when everything was very close, very hot, and very alert. Explaining the equations of ancient physics, about 14 billion years ago, the temperature and density of the universe stopped. But as we grapple with this topic, it becomes clear that the situation may not be as simple as it seems. Current evidence suggests that Einstein's equations are not related to unity. The observations point to a critical time, before 32-10 seconds after the Big Bang, when the universe formed rapidly in what is known as the expansion of the universe. This period of expansion provides important insights into the universe's vastness, explains what a smooth universe looks like, and explains the formation of galaxies. But despite the concept of inflation, independence remains a challenging concept. Extreme density and temperature bring quantum forces into play and disrupt our understanding. A general relationship alone may not be sufficient to fully understand the specific situation. The early period of rapid expansion helps solve some of the mysteries of the Big Bang theory, but also prompts a re-evaluation of our understanding of the universe's expansion and origin of the world. A different kind of specificity indicates that it may not show the whole picture. Mathematical specificity indicates gaps or limitations in theory. In particular, the clash between general relativity and quantum mechanics highlights the need for further understanding. As we delve deeper into this cosmic mystery, we see the ideas of the famous physicist Sir Roger Penrose, who proposed a new framework that challenges our understanding. Penrose suggested that major events in the formation of the universe, including the formation of galaxies and stars, may have occurred before the Big Bang itself. This provocative idea opens up new avenues for exploring and questioning the foundations of our cyberspace. In this broader context, the end of the world remains a philosophical issue. As we fast forward through time to infinity, we face the infinite nature of these particles, suggesting a world dominated by photons as black holes shrink. Photons, following arbitrary landmarks, travel along paths without time or space. In essence, it is instantaneous and crosses the fabric of space-time without affecting time. To demonstrate this, consider turning on a light for a short time and then turning it off. The time when the candle exits the candlestick represents event A, and the time it reaches a point further away from the candlestick represents event B. The time interval between these events are calculated using the equation ds(2 = 0. Since the light bulb travels simultaneously from event A to event B, crossing time and space by canceling the net change in space-time. This unique feature of the images, without a rest frame and self-clocking, is consistent with a fundamental principle of physics, the constant speed of light. No matter where you are or how you are moving, the speed of light will always be fast. If the images have a fixed reference point, the light will not move from its point of view. This fact challenges our understanding of the speed of light and shows the unusual nature of the images. The governing light equations, also known as Maxwell's equations, are interesting and always different. This means that the equations remain unchanged whether the system is scaled up or down. Basically, the universe, or small scale of quantum particles, when described by these equations, looks the same. Using this picture in conjunction with the theory of the Big Bang, we can imagine a situation where the initial state of the universe is outside the traditional theory of the Big Bang singularity. This mathematical approach allows us to describe the beginning of the universe back to infinity. Einstein's theory of relativity provides important knowledge to understand the time of the beginning of the universe. According to Einstein, energy and mass are related, and this relationship is further explained by Max Planck's equation, which deals with energy and frequency. This continuity between mass and frequency emphasizes the role of mass in determining the passage of time. When we think about the future of the world, we imagine a situation where the world is empty, filled only with images. At this time in the future, the universe may resemble a new phase of the Big Bang, representing a revolutionary phase in the evolution of the universe. Known as coherent cyclic cosmology, this theory challenges conventional ideas about the beginning and end of the universe. It represents a continuous cycle of expansion and contraction, each cycle mirroring the previous cycle. This change model emphasizes the importance of the Hubble parameter, which measures the expansion rate of the universe. As the universe expands and contracts in a continuous cycle, driven by the interplay of dark energy, it embodies a timeless and interconnected reality where past, present, and future intertwined in our day-to-day lives. Time flows continuously, shaping our experiences as a sequence of moments or snapshots. Each moment unfolds, leading to the next in a never-ending cascade of events. If we were to envision all these moments lined up, every earthly occurrence and every event in the vast expanse of the universe would capture the entirety of cosmic history, from the explosive birth of the Big Bang to the formation of stars in the Milky Way, from the emergence of life on Earth billions of years ago to significant events happening as we speak. They all coalesce into our sense of now. But Einstein's theories of relativity introduce a fascinating twist to this seemingly straightforward concept of now. According to special relativity, an entity's perception of time can differ depending on its motion. This means that individuals in motion will experience time differently and may slice through the fabric of space-time at varying angles, shaping their unique now slices. To illustrate this, imagine a device in a distant galaxy billions of light-years away from Earth. As the creature moves away from Earth, the now cuts through that region of space-time in a different direction, restoring its present to the history of the world. But if the entity moves to the world, its now phone will be attached to the future world, showing things that haven't happened yet. This concept becomes particularly interesting when applied to photons, light particles. There is no prior, current, or historical meaning to the images.